start the recording. So today we are covering, or at least starting to cover, we'll see what happens, Gaussian integers. Now I had 2 days marked down for this, and of course we had the day we missed there, right? So I'm not 100% sure what to do about that. I feel like I should add a Friday somewhere, but this Friday is not good because like Audric's gone, So maybe you're gone too. Maybe next Friday. Dang it. So maybe I'll make a video this Friday, or next Friday, or sometime to fix the schedule, which I hate to do. Making a video is more work. But anyway, chapter 6 in your book's okay, right? But this blurb, as it's called, by Keith Conrad on the Gaussian integers is just masterful, and I think we'll benefit greatly from just following this. I think it's really, the proofs in it I think are more clear than the ones in parts of chapter 6. So let's get to it. So what are the Gaussian integers? And why are we studying them? Well, in short, because they're going to reveal many interesting facts about ordinary integer primes. And so this is, and they'll also give us a way to derive the Pythagorean formulas we found before. That also happens here. And besides all that, they're just interesting for their own right. Okay, so definition. Z adjoin I is the set A plus BI such that A and B are integers. So technically, this is a subset of the complex number system, right? So we can do complex arithmetic in here, all right? So do you guys know complex arithmetic a little bit? Like complex number calculations? You've seen them before, right? Okay, good. So definition. For A plus IB in the Gaussian integers, its norm, and we're calling this, by the way, so we gave this name alpha equals to A plus IB. All right, let alpha equal to A plus IB. Its norm, all right, is the product n of alpha equals to alpha complex conjugate. All right. So let's work out that, right? So that's A plus IB times A minus IB, right? Which works out to A squared plus B squared, because when we multiply that out, we get A squared plus IBA minus IBA, and then minus I squared B squared. But minus I squared is 1, so we just get plus B squared. All right? So this is the norm. Now, so when I first taught number theory, it bothered me that they called this a norm, because this use of the word norm is at odds with the use of a norm in linear algebra. There's no linearity here. It's actually pretty nonlinear. So for example, the norm of 3 is 3 squared. So the norm of 3 is 9. Another example, the norm of 1 plus I is 1 squared plus 1 squared, so that's 2. All right. Just a couple examples. Now, the norm is useful because you notice that the norm is an element of what? Yeah, it would be the natural numbers, but I'll just say it's an element of z. But you're right, we could say z plus if you like. Although I guess it could be 0 if we put in 0, so I'll just say z. But yeah, usually natural number. Okay, so, and that's usually something that number theorists want for their norm. If they're putting a norm on an abstract system, they want it to be integer valued, so they can study things about the integers using that algebraic structure often. All right, now we have the following theorem, 1.2. And by the way, I have posted this in course content for you guys. It is also available freely online at Keith Conrad website. This is his blurb on the Gaussian integers. If you Google it, you'll find it. If you try to find it in his web page, you might not, because he has so many things posted there. But anyway, the norm is multiplicative. All right. And by that, I mean that n of alpha beta is n of alpha times n of beta. It's multiplicative, like the Euler phi function, right? We worked with that multiplicative function. I'm going to give a proof of this, which relies on the arithmetic that we know in complex numbers. So my proof is not the one he gives. So the norm of alpha beta is by definition alpha beta times what? Times alpha beta conjugate. But one of the fundamental properties of complex conjugation is that the conjugate of the product is the product of the conjugates. So this is exactly alpha beta bar, beta bar. The properties of complex conjugation. And then, of course, complex numbers commute, so we can reorder these. And I have alpha alpha bar and beta beta bar. In other words, I have n of alpha times n of beta. We're done. The norm is multiplicative. In fact, the norm is the square of the length of the Gaussian number as a complex number, right? It's nothing more than that, right? If you look at it, this is the squared length of the complex number a plus ib, distance from the origin, right? It's nothing more than that. What more can I say? What's the analog of the norm in the integers? What are we generalizing here? What serves the role of the norm? How do you tell how far an integer is from the origin? Right, absolute value plays the role of norm in the integers. So, all right, so corollary. (1.4). The only Gaussian integers which are invertible are plus or minus 1 and plus or minus I. All right. Okay. So to start the proof here, it's easy enough to prove that all of these are invertible, right? So like 1 times 1 is equal to 1, minus 1 times minus 1 is equal to 1, right? I times minus I is equal to 1. So this shows that they're invertible, right? The inverse of 1 is 1, the inverse of minus 1 is itself, the inverse of I is minus I. Now the claim, though, is that's it. That's it, right? So the converse direction, so suppose, alpha equal to a plus ib has inverse beta equals to c plus id, right? With what? Alpha beta equal to 1. So why is this a corollary to this theorem? It's because the proof here relies strongly on the norm. What happens when you take the norm of alpha beta equal to 1? What does it show you? I feel like I'm getting off track here. I better go back to...
Well, inverse of 1 is just 1.
Ah, I see. Well, the inverse of 1 is just 1. Well, we don't know that. I mean, this is a new number system. We don't know what... I mean, that doesn't say that the inverse of... This equation... I mean, rational numbers, this could be 2 times a half equal to 1. I mean, whatever.
Yeah, but okay.
So check this out. So n of alpha times n of beta, right, is equal to n of 1, which is 1. N of alpha and n of beta are integers. How can you have... Is that your backpack?
Yes.
Okay.
All this is mine.
It's all yours. I don't know. Who's that dude? All right, anyway, so it's probably... Maybe he's trying to get into the other room. I don't know. The product of two integers is 1. What does that say about the integers? How can you get the product of two integers equal to 1? Yeah, but what are the only units in the integers?
1.
And 1 and negative 1, right? But can it be negative 1? Well, no. Remember, as you pointed out up here, fundamental observation, n of alpha is greater than or equal to 0, right? So it can't be. So it must be that n of alpha equals to n of beta equals to 1, right? So the only way we can have a unit is if it has norm 1. Okay, so then what? Well, norm of alpha is a squared plus b squared, right? So you have a squared plus b squared equals to 1. We're taking a and b to be integers. So clearly, you cannot have a or b 2 or beyond. That just violates the equation. Our only choice is to have one of them 0 and the other one of them plus or minus 1, right? And that gives you the 4 things we've listed, namely 1, minus 1, I, and minus I. So this implies a comma b are elements of minus 1, 1, which implies a comma b is an element of, well, a plus ib. Well, it says alpha is equal to plus or minus 1 or plus or minus I, right? Okay, so there we go. Proved. So again, there are 4 units, right? These are also invertible elements. Another word for this is units, right? So the units of the Gaussian integers are namely plus or minus 1 and plus or minus I. This is important because as we're studying factoring in the Gaussian integers, questions about factoring are going to be ambiguous up to multiplication by a unit, all right? So, and also interesting, in future lectures, when we're beyond this and we start studying the algebraic integers, we're going to find that there's also a norm there. But the difference is when pretty much the same calculation is going to happen, but when we go to solve the equation, norm of alpha equal to 1, it's going to be a Pell's equation in one example. And so for the one that works out the Pell's equation, you have infinite solutions. You have infinitely many units in that system. Another one's more like this. Like the typical examples have a finite number of units, the ones we look at in here. Anyway, more on that later. So let's talk about divisibility. See, because what we're going to see today is there's a mirroring of all the things we've learned for integers for Gaussian integers. So section 2, divisibility. Can't spell. Divisibility. All right. So the definition we should settle, right? We say beta divides alpha if there exists gamma such that what? Alpha equals what? Alpha equals beta gamma, right? And of course, what am I talking about? I'm just using letters at the moment, but what I mean to say there, of course, is context here. I'm supposing that alpha and beta are where? Gaussian integers, right? And this gamma, again, right? Also a Gaussian integer, right? So this is, my point to you is we define divisibility, divides by, in the Gaussian integers in the same way that we defined it in the integers, okay? To say that b divides alpha is to say that alpha is a multiple of b, a Gaussian integer multiple of b. So some examples he has for us here, which I will steal because they're nice and I don't have to think. Example 2.1. He has 14 minus 3i equals 4 plus 5i times 1 minus 2i. All right. So this shows us what? 4 plus 5i does what? It divides 14 minus 3i. Okay? Example 2.1. 2.2 rather, he asks a related question. He says, okay, so we just saw that 4 plus 5i divides 14 minus 3i. So he asks a related question. What about 4 plus 5i? Does it divide 14 plus 3i? All right? So what we're going to do is to actually divide. So check it out. Do you guys know how to divide complex numbers? Well, I'm about to refresh your memory. So we're going to take 14 plus 3i, and we're going to divide by 4 plus 5i. This is something we can do. These are complex numbers. Like rewriting this as a fraction, what would this look like? Well, trying to think here. Which one's the 4 plus 5i? Which one's the 14 plus 3i? Alpha is the alpha, and 4 plus 5i is the beta. So what we're asking is, can we do alpha over beta equals to gamma? Like this is equivalent to that, assuming, of course, that like beta is non-zero, right? But let's suppose beta is non-zero. So in other words, we can check divisibility by checking if the fraction, if the quotient, alpha over beta, is actually a Gaussian integer, right? If it is a Gaussian integer, we're good, because we can multiply the fraction and get back the original divisibility condition. If when we calculate the fraction we don't get a Gaussian integer, well, game over. So let's do it. So the trick is you multiply by the conjugate of the denominator to rationalize, right? So 4 minus 5i, 4 minus 5i. Now when you multiply the downstairs, I don't even think about the multiplication, guys. I just do it. It's 4 squared plus 5 squared. It's 16 plus 25. It's 41. So I got 41 in the denominator, I believe.
You just take the norms of both and do that?
Well, it's the number times its conjugate, so it's its norm.
Oh, okay.
Yeah. And then upstairs.
Yeah, so you can just do the a squared plus b squared trick.
Exactly. Yeah. Yeah. And if you think about it, whenever you do this complex number calculation, it's always like that. Like here's the formula. Let me stop. So 14 times 4 is 56. And then I've got 14 times 5 is 70. So minus 70i plus 12i, right? Minus 15i squared, which is plus 15. So 56 plus 15 is 66 plus 5 is 71. And 70 minus 12 is 58. So minus 58i divided by 41. This is not an element of the Gaussian integers, because 71 over 41 and 58 over 41 are not integers. Okay? Therefore, 4 plus 5i does not divide 14 plus 3i. That's at least a little bit interesting, because you notice that the norm of 14 plus 3i and the norm of 14 minus 3i are equal, right? So that's already kind of a cautionary tale. Norms being equal don't mean things work out the same. We can already see that here. Let us move along. Theorem. .3 alpha equals to a plus ib in the Gaussian integers is divisible by c and z, an ordinary integer, all right? If and only if c divides a and c divides b in z. So notice he's talking about divisibility in the integers, the thing you guys prove stuff about on the test. Right. All right, so prove this thing. It seems like a very reasonable claim, doesn't it? So let's see how it goes.
Oh yeah. Can you just say like, oh, not in general, but I mean you could just always pull out that constant if it did divide both.
Let's see here. So let's start with the forward implication, right?
Yeah.
To say c divides a plus ib, right, in zi, the Gaussian integers, implies what? That there exists m plus in, right, in zi such that what? A plus ib is equal to c times m plus in, right? A plus ib has to be a multiple of c. But that is equal to cm plus icn. And remember, two complex numbers are equal only if their real and imaginary parts are equal, right? So this complex equation gives me two real equations. In particular, it gives me a is equal to cm, and it gives me b is equal to cn, which of course implies c divides a and implies c divides b. Okay, so that's the first half. So we got the forward implication of the theorem, right? Now, conversely, suppose c divides a and c divides b, then there exist m and n in the integers such that what? A is equal to mc and b is equal to nc, right? Thus, a plus ib is equal to mc plus inc, which is equal to c times m plus in. Therefore, c divides a plus ib. You probably could change my wording a little bit and make this a biconditional proof, you know? But anyway, there it is. I think his proof is biconditional. All right, yeah, I think it is. Oh well. So he says taking b equals to 0 in theorem 2.3 tells us that divisibility between ordinary integers does not change when working in Zi. All right. So in other words, everything we know about divisibility of integers, all those things are still true for the integers that are sitting inside the Gaussian integers. All right. That brings us to theorem 2.4. And theorem 2.4 is very useful for Gaussian integers alpha and beta. All right. For Gaussian integers alpha and beta. All right. If beta divides alpha in Zi, then n, the norm of beta, divides the norm of alpha in Z. Proof. So suppose beta divides alpha, then there exists gamma in Zi such that what? Alpha equals to beta gamma, right? Thus, n of alpha equals to n of beta gamma, but by the multiplicative property of the norm that we proved, this is n of beta times n of gamma, right? These are all integers. This equation proves what? It proves that n of alpha is a multiple of n of beta, which is to say that n of beta divides n of alpha, right? So there it is. Corollary to this theorem, 2.5, I think, is the following. And this is pretty interesting. Kind of a surprising corollary in some sense. A Gaussian integer has even norm. If and only if it is a multiple of 1 plus I. So we'll do the converse direction first, right? It's kind of easy. So if you have like gamma is equal to, say, alpha times 1 plus I, then what's the norm of gamma equal to? It's the norm of alpha times the norm of 1 plus I. But what's the norm of 1 plus I? As I pointed out earlier, 2, right? So that shows you that the norm of gamma is even, right? Because it's twice an integer, right? That's an element of 2z. How about the other direction? So what should we do? We should suppose the Gaussian integer has even norm. I guess I'll use gamma again. I'm going to call it a plus ib because I suspect we need to get into it. Suppose gamma equal to a plus ib has, n of gamma, which of course is a squared plus b squared, is an element of 2z. How to prove that is a multiple of 1 plus I? Now he points out, he's like, okay, so that means that, notice, a squared plus b squared equals to 0 mod 2. And then he says, by taking cases, we see this means that A and B, he uses M and N, I'm changing his M and N to A and B. This means A and B are both even or both odd. Let's think about that. If you have m squared plus n squared equal to 0, and you're working mod 2, you can either do 1 and 1, because you get 0, or you could do 0 and 0, which gives you back 0, but you can't have 1, 0, and you can't have 0, 1. So this implies A equals B equals 0, or A equals B equals 1 mod 2. Which is to say that they're both even or both odd, right? Because mod 0 is even, mod 1 is odd, mod 2. Returning to the original interpretation in terms of integers. All right, now here's the trick. There's got to be a trick. He's like, we want to write, wish to write a plus ib, right, equal to 1 plus I times something, right? Let's say u plus vi. But this is equivalent to wanting what? We want a plus ib equal to, he says it's the same as u minus v plus I times u plus v, or u plus v times I. I never know whether to put the I on the right-hand side or left-hand side, whatever. That's just multiplying the equation out above, right? So what's the solution? Oh, this is an algebra problem. This is just straight up linear. This kind of stuff. Check it out. It's not bad. So we're solving a equal to u plus v, and b equal to u minus v, rather. B equal to u plus v, right? So how do you solve that for u and v? We're trying to solve for u and v, right? So add the equations. What happens? To u, right? From the plus, subtract the equations. What do you get? Minus 2v, right? So we find u equal to 1/2 a plus b, and v equal to 1/2 b minus a, right? And now the thing is, those look like fractions. So why should those be allowed? Well, think of, what's that?
Just makes it even.
Right, because remember what the possibilities are for a and b. They're either both 0, in which case u and v are both 0. Or what? They're both 1, in which case you get 2. Well, you get 2 over 2, which is 1, or you get 0. And so that shows that it's a multiple of 1 plus I, because these solutions solve the problem. An example, I think it's nice to see an example, 2.6. Here we have 1 plus 3i. The norm of 1 plus 3i is what? It's equal to 10, right? Even norm. 10 is even. That means we can write 1 plus 3i as a multiple of 1 plus I, right? Now, if we believe in our proof, we can even say, I think we can even write down maybe, can we? Or is it still 2 mod? Is it 2 mod 2? Is that the, do those formulas actually work? I think they actually work. Like 1 plus 3 is 4. 4 divided, well, I'm going to write down what he has. He says this is equal to 2 plus I. I'm not sure. I think that,
Yeah, it is.
it does work, right? Because
Yeah, because the i's cancel out that extra 1.
oh yeah, so see a plus b here, a is 1 and b is 3. So we get 4 divided by 2 is 2. And 3 minus 1, 2 over 2, I. So yeah, actually, the proof of this corollary, not only does it show you that it's a multiple, it shows you how it's a multiple. These formulas right here. So that's kind of neat. And another example, the norm of 1 minus I is also 2, right? So notice that 1 minus I is equal to 1 plus I times what? Well, we can figure it out, right? So looks like A is 1, B is minus 1, so the U is 0, and the V is 1, right? So that means I. That's wrong.
No, it's not.
Well, that doesn't work out, though. I think I've somehow neglected a minus in my formulaics. That's supposed to be minus I. So think through that. The B is minus 1, and the A is 1. So it's minus 1, which is minus 2 over 2, which is minus 1, if I was more careful. Anyway, do you need that stupid proof formula to figure that out? No, I think you could factor out a minus I to see this without all that technology. I mean, I certainly could. All right. And all right, so what he says next, he says, so Theorem 2.4 is a quick way of showing when one Gaussian integer does not divide another, because we can check divisibility of the corresponding norms. So this is an amazingly efficient way to check on things. Let me show you his example. So he's like, he's like 3 plus 7i divides, I lost my place, curses, 10 plus 3i, question mark, right? Well, you guys tell me, what's the norm of 3 plus 7i? What's the norm of 10 plus 3i?
9 plus 49 is
58?
58. Yeah, 9 plus 100 is 109.
All right. So I heard we got 58 for the first one, 109 for the second one, right? So the question is, does 58 divide 109? Because if this was true, this is a necessary implication of it. But this is false, right? Therefore, 3 plus 7i does not divide 10 plus 3i. All right. Of course, the converse is false. So here's an example of how the converse is false. Alpha equal to 14 plus 3i. Beta equal to, what would the converse be, by the way, guys, while I'm writing this out? 4 plus 5i. The converse would be what? If the norms are divisible, then the corresponding Gaussian integers are likewise divisible. This is false. So here's an example of that. So we have alpha, we got beta. N of alpha here is, 205, you got it, it's 205, which, by the way, is equal to 41 times 5. N of beta is 41. So in this case, 41 divides 205. In other words, N of alpha divides N of beta. That's true. However, how do we check if, remember, we can do what? We do, well, yeah, we can calculate the fraction, right? Oh, in fact, we already showed. This is the one we did before. We already showed that 4 plus 5i does not divide 14 plus 3i. That's the one we worked the fraction out for, actually. So, thank you, Conrad. That was helpful. It didn't make me make up another example of those. All right. He says, the foolproof method of verifying divisibility in the Gaussian integers is testing if the ratio is in the Gaussian integers after rationalizing the denominator, just like we did in the example 2.2. He says, the norm divisibility check in Z is a necessary condition for divisibility in Zi. And when it fails, so does divisibility in Zi. But it's not sufficient anyway. All right, so.
Okay, so what he's saying is if the norms are not divisible, then we know for sure that the corresponding integers are not divisible.
Gaussian integers, yeah.
Just because they are divisible does not imply that
right.
the Gaussian integers.
The theorem goes one way but not the other.
Yeah.
So next thing he's talking about is unit multiples. So talk a little bit about unit multiples. All right, so like in Z, the integers, right? If you have absolute value of m equals to the absolute value of n, then what does that tell you about the integers? Right.
Ooh, wait, no.
M is equal to, well, you almost got it, plus or minus n, right? Because the absolute value eats minuses. Now, the corresponding statement in the Gaussian integers is false. In other words, like looking at, I'm saying look at this as unit multiples, okay? Because that's what plus or minus is in Z, right? So it is not the case that n of alpha equals to n of beta implies that alpha is equal to a unit times beta, where u is plus or minus 1 or plus or minus I. It is not the case. All right. So the example he gives of this is really nice. I really like the way he points out. So he's like, if you look at 4 plus 5i and 4 minus 5i, both have norm what? 41, right? So how can I prove that 4 plus 5i is not a unit multiple of 4 minus 5i? Well, you got 4 units, so check it out. So 1 times 4 minus 5i is 4 minus 5i, right? minus 1 times 4 minus 5i is minus 4 plus 5i, right? I times 4 minus 5i is 5 plus 4i. Minus I times 4 minus 5i is minus 5 minus 4i. So you look at it, step back. Is there 4 minus 5i in that is there 4 plus 5i in that list? Is 4 plus 5i in that list?
4 plus 5i.
Yeah. So you notice 4 plus 5i absent, right? Which goes to show you, here's an example. These two Gaussian integers have the same norm, but they are not unit multiples of one another. All right, so we can't even see that from equal norms. All right. Like, well, what good is the norm if we can't even say that? You know? Well, let's see. Let's see what good it is.
Couldn't we say like they're vector away from the norm is equal magnitude? Like if you use A and B as components.
Yeah, you could say that they have the same distance from the origin as complex numbers.
Yeah.
You can say that. Needly doodly. That certainly could be said. And many other things, I suspect. So next up here, Theorem 3.1, the division theorem. All right. It says the following. For alpha and beta in the Gaussian integers, with beta not equal to 0, there exist gamma and rho in the Gaussian integers such that alpha is equal to beta gamma plus rho. And n of rho is less than n of beta. In fact, we can choose rho so that the norm of rho is less than or equal to 1/2 the norm of beta. This is the division theorem. So I'm not going to prove this right away. We're going to work through a couple of examples to understand what's going on here before we attempt a proof, all right? So here's the example he has for us. It's a good example for a lot of reasons. Alpha equals to 27 minus 23i, and beta equals to 8 plus I. All right. The norm of alpha. Well, he doesn't tell me what the norm of alpha is. It's pretty big. The norm of beta is what we actually have to worry about. The norm of beta is 64 plus 1 is 65, right? So we want to find, we wish to do what? We wish to find gamma such that what? Such that alpha is beta gamma plus rho, with the norm of rho being what? 1/2, right? 1/2 of 65, which is what? Well, it's 60, yeah, 32.5, right? Yeah. So the norm of rho can be at most 32, since it has to be an integer, right? All right. Assuming that 32 can be reached as a sum of squares. I don't know if it can. But anyway. Okay, so basically, this beta is the dividing number, right? Rho in this whole story is playing the role of the remainder, right? And gamma, well, it's essentially the quotient, right? So like, this is alpha over beta equals to gamma plus rho over beta, right? If you want to rewrite this in terms of fractions. See that? Divide the equation of the theorem by beta. That's what we're trying to do. That's why this is called the division theorem. So what we should calculate then is alpha over beta, right? So let's calculate. And that's something we can do because, again, these are complex numbers. So what is alpha over beta? Well, that's 20 alpha over beta. I've lost my ability to write beta. That's 27 minus 23i divided by 8 plus I. Right? So we do our standard trick. We multiply by 8 minus I times 8 minus I, right? So downstairs we're going to get 65. And upstairs we're going to get 193 minus 211i. And work out the math. All right, and just, what's helpful in these kind of things is to use decimals, right? So note 193 over 65 is equal to 2.969, dot, and minus 211 divided by 65 is equal to minus 3.246, dot. So in the study of the division algorithm over positive integers, if you do it really carefully, you will use what's called the smallest, the greatest integer function to choose. And so, like, if we were to use that here, we would pick, as he points out, you would try from this. Maybe you'd try 2, and the greatest integer here is minus 4. And those would be bad choices, because if you did that, if you did try gamma is equal to 2 minus 4i, we get alpha minus beta times 2 minus 4i. Well, it works out to 7 plus 7i, right? And the norm of 7 plus 7i, what's that? This would be our rho, right? And the norm of that rho would be 40, what is it actually? 98, 49 plus 49, right? Of course, that's no good, right? So we can't just pick the integers using greatest integer function. Like, that's definitely not what you want to do. What you probably already have an intuition for what we should have done. What should we have done instead of picking 2 and minus 4? That did not work. Yeah, like what should we have picked instead of 2 and minus 4? These were both picked on the basis of using the greatest integer function, which is sometimes used in setting up the division algorithm in the integers so that you get a unique remainder. so that the division algorithm is unique. All right, but we're actually about to lose that uniqueness here. But I mean, I think the clear choice is, can I erase the wrong, would you guys get it? Because it's going to be in the way. Got it? Okay. So instead of picking 2 and minus 4, what we should do is pick the integers which are closest to the decimal form, right? Like we should pick 3, you know? And this one we should pick what? Minus 3 maybe, right? So I'm suggesting that gamma should be chosen to be 3 minus 3i, right? Then you calculate what's beta gamma. What's 8 plus I times 3 minus 3i? Well, I'm going to factor that 3 out. Oh, fine, I won't. I don't know what I'm going to do. I got 24 plus 3 plus 3i minus 24i. I get 27 minus 21i, I think. That seems bad. Did I do this wrong? Oh, well, that's beta times gamma. But I have to subtract, I have to ask, that doesn't tell me what rho is, right? Now I have to do what? Alpha minus beta gamma. Duh. Right? Rho is equal to alpha minus beta gamma. So what's alpha minus beta gamma? So subtract this from alpha. 27s cancel, and you get minus 23 minus a minus 21, which gives you minus 2i. So that's my rho, and the norm of rho is 4. 4 is definitely less than 32.5. So we have achieved, and what we've done is we've shown that this theorem can be implemented for these two numbers, right? In this case, the remainder worked out to minus 2i. The quotient, gamma, we chose to be 3 minus 3i, and there it is. And so, so here's a comment here, is that you could look at 34 as 9 times 4 minus 2, but you could also look at 34 as 9 times 3 plus 7. So what this comment is about is that if we think about the division algorithm in the integers, if we didn't insist on, like a positive remainder, we could choose a smaller remainder in terms of absolute value, right? If we wanted to, but we don't. Why? Because we are always working with positive integers, right? So essentially we have dodged discussion of the norm and the integers by just making an ad hoc reduction of the whole discussion to positive integers, right? Now we can't do that with the Gaussian integers. Like there's no such sort of ad hoc reduction to make the thing simpler. The fact of the matter is that as we go through these constructions, we're going to see that they're ambiguous in the sense that there's not just a single choice for the remainder. You could maybe choose a few different. There may not be just one choice for gamma. There might be